This entire week is dedicated to optimization problems because they are so much fun. We get to figure out the best way to do stuff. Practical problems often involve figuring out the best way to do something. That's what calculus is good for. Steps in problem solving. Understand the problem. So read it carefully. Maybe circle stuff, get a highlighting pen, figure out exactly what you're looking for and what you have to have in order to get that. If you can draw a picture, draw a picture. Sometimes you can't. Introduce notation, so label stuff, name your variables. And you're going to come up with a quantity that is to be maximized or minimized. And we're calling it Q for now. That is our objective function. Then we want to express the objective function in terms of the symbols that we introduced. There's also going to be a constraint function. Then we use the constraint function to rewrite the objective function with just one variable in it. Then we use the previous methods to find whether we have a max or a min. You can use the extreme value theorem, you can use the first derivative test or the second derivative test to see if you have a max or a min. So let's look at a simple example. A farmer has 2,400 feet of fencing, wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field with the largest area? So we've read it carefully. You might highlight some things or circle some things. The fact that they have 2,400 feet of fencing, the fact that he wants to have the largest area. So our goal is to maximize area. Now, first thing I'm going to do, here's my river. Here's my fence. And we're going to pretend that it's a rectangle. And I'm going to name this side Y, and that side X. I usually go ahead and label each and every side. And then this side is also X, but we don't need any fence there. So if I'm writing down my constraint, that is 2 Y's plus an X have to be equal to 2,400 feet, because that's how much fencing I have. The constraint is always going to have a number on one side of the equal mark. We want to maximize area, so my objective function, area is equal to X times Y. Notice the objective function doesn't have a plain old number on either side of the equal mark. It has a function name equal to something with variables in it. But it has two variables in it. So I want to take this function with two variables and write it with one by using the constraint. So 2,400 is equal to 2y plus x. And just because I'm a fan of the x, I'm going to write everything with x's in it. So y is equal to 1,200 minus x over 2. Easy enough. So now I take this and I put it into my objective function. Area is equal to x times 1,200 minus x over 2. Distribute, because I want to get it as simple as I can before I start differentiating. And now I'm going to go ahead and take the derivative. Let's see, 2 falls down. Subtract 1 from the exponent. How convenient, that cancels. And then I'm going to set that equal to 0 because when the derivative is 0, that's where maxes and mins happen. Well, that was easy. X is equal to 1200. But is this a max or is this a min? So, couple of ways, actually 3 ways we can decide. We can use the extreme value theorem. So we have to know the domain of x in order to use the extreme value theorem because we have to have a continuous function on a closed interval. Well, x, which is the length of the fence that is parallel to the river, could be 0, which would be stupid. Then your area would be equal to 0 because x times y would be 0. Your x could be 1200, in which case y would be equal to 1200 minus, 1200 over 2. So 1200 minus 600, so my area would be equal to 1200, I'll clear out old stuff, times 600, wow, 720,000. Or I could use all my fencing for x, which would be stupid, but I could do it. Then y would be equal to 0, so the area would be equal to 0. So this is definitely a max. Now let me go back and make sure, yes, it's feet. Another way we could do it is the first derivative test. I plot my 0 here, which was 1200. I look back at my derivative function, 1200 minus x. I plug in something less than 1200, something like 1100, I get a positive thing. I plug in something bigger than 1200, 1300, I get a negative thing. So I have a max. The other option is the second derivative test. If I take the second derivative, 1200 minus x, the second derivative is negative 1, which is less than 0, which means I'm concave down, which means I have a max. So you have 3 options: extreme value theorem, first derivative test, second derivative test. Now that we've gone through and done this, let's go back and make ourselves a little checklist of what we did. First thing we did, read carefully and draw a picture. Your picture doesn't have to be beautiful. It just has to help you figure out what's going on there. Next thing we did is we took the information from that paragraph and wrote down an objective and a constraint. Well, we introduced some variables. Let's go ahead and write that down. So you can't have a constraint and an objective without variables. I usually do that as I'm drawing the picture and as I'm writing them down. So introduce variables. I usually try to make them meaningful. Write a constraint. It's going to have a number on one side of the equal mark. And an objective. Something you can take a derivative of. Then you're going to use your constraint to rewrite the objective with just one variable in it. Then we'll differentiate. Set it equal to 0 and solve. Then we make sure we have what we really wanted. If we have a max, if we wanted a max, we have a min if we wanted a min. And then you'll write a sentence or something, answer the question. So we'll use these steps as we go through and answer all of these questions. Now example 1, yeah, it has some pretty answers for you. It goes through and shows some options. Then it labels it, kind of like I did, except it used X's on the sides. But you end up with the exact same answer. And they showed using they call it the closed interval method, which is the extreme value theorem that we learned. Just a reminder of the first derivative test and the second derivative test. You used those for your curve sketching lab, so you should be familiar with those. Let's do a couple more examples. So read over number 16. Rectangular storage container with an open top. It has a volume of 10 cubic meters. So immediately you're thinking, okay, volume is my constraint. It's got to have 10 cubic meters. The length of the base is twice the width. Material for the base is $10 per square meter. Materials for the sides are $6 per square meter. And we want to determine the cost of materials for the cheapest container. So we want to minimize cost. So first off, I know my constraint is the volume. This is number 16. And I know that it is a rectangular storage container. There's my gorgeous picture of a rectangular storage container. So here is height, length, and width. You could use X, Y, and Z if you want. I don't care. I use L, W, and H. So volume is equal to length times width times height. And that has to be equal to 10. I have a constraint as a number on one side of the equal mark. We also know that the length of the base is twice the width. So L is equal to 2W. So let's go ahead and make volume a little simpler. Since L is equal to 2W, that means I can replace that L with 2W times W times H, which is 2W squared times H, has to be equal to 10. Okay, getting better. Now I'm down to two variables. I need a cost function because my goal, my objective, is to minimize cost. So let's make a cost function. Material for the base is $10 per square meter. It has an open top, so I only have one base. That's $10 times this base is L times W, but L is 2W, so it's 2W times W. That's the cost of my base. I have two sides who are L times H. So I have this one and the one opposite that's on the back of the box that are L times H. They cost $6 per square meter. There's two of them, and they are L, which is 2W, times H. Then I have these other sides that are W times H. They cost $6 per square meter. There are two of them, and they are just W times H. So let's simplify that as much as we can before we go back and make it into one variable. I have 10 times 2 is 20. That shouldn't be an equal mark there. That should be a plus. Because I think I'll be able to get it on one row now. I have 6 times 2 times 2, 24WH, and 6 times 2, which is 12WH. And I can combine all of that into 20W squared plus 36WH. Now I need to rewrite it with one variable. I have my constraint with the 10 on one side of the equal mark. I have my objective function, cost, which is something I'll be able to take the derivative of. And now I am going to rewrite this with only W's in it. So 2W squared H is 10. H is 10 over 2W squared, which is equal to 5 over W squared. So my cost function is equal to 20W squared plus 36W, and height is 5 over W squared. Simplify 20W squared, 36 times 5, won't try to do it in my head, I think it's 180. 6 times 5, oh, I was right, yay me. 180, I have one W on top, two W's down below, and because I know I am about to take the derivative of it, I'm going to go ahead and write it as W to the minus 1 power. So C primed is equal to 40W minus 180 W to the minus 2 power. I'm ready to set it equal to 0. And at that point, I go ahead and rewrite it as 180 over W squared. When I set that equal to 0, I have 40W equals 180 over w squared. So 40w cubed is equal to 180. W cubed equals 180 over 40. 18 over 4 is 9 halves. I don't need to use the calculator for that. So W is equal to the cube root of 9 halves. That's the exact answer that WebAssign would want, but I have no idea what length the cube root of 9 halves is. So let's take 9 over 2 and raise it to the 1/3 power. And I get something that's really close to 1.65. Now I need to make sure that what I have is actually a minimum and not a maximum. So you can either do the first derivative test. I usually make myself a little number line. I plop my cube root of 9 halves on there. I plug in something smaller than the cube root of 9 halves, something like 1. Then I would have 40 times 1 minus 180 over 1, which would be a negative thing. Then I put in something bigger, something like 2. So if I put in 2, I would have 40 times 2 minus 180 divided by 4, which gives me a positive thing, which means I have a minimum. Option, second derivative is equal to 40 plus 360 over w cubed, which is greater than 0, which means I'm concave up like a cup, which means I have a min. And now I can use this w to go back and find my length and my height, because w is equal to 1.65, length is equal to 2 times that, about 3.3, and then the height would be equal to 5 divided by 1.65 squared, so about 1.84, and all of those. Are in meters. Okay, number 35. I'm going to let you do this one, and then we'll meet back and compare answers in a moment. Alrighty, here's my picture. I made my horizontal x's and my vertical lengths y. The constraint, or the margins, were 8 on the top and bottom and 4 on the sides, yeah. And the printed area was constrained at 384 square centimeters. So my objective was to minimize the total area of the poster. So my width had to be x plus 4 on this side and 4 on that side. My height had to be y plus 8 on top and 8 on the bottom. I multiplied, I simplified, and I ended up with 8 times the square root of 2. Again, WebAssign is probably going to want exact answers, but I have no idea in my head how long 8 times the square root of 3 is. So I like to write it down as a decimal answer. And then I checked both ways. You only have to do one way. You only have to check one way. either first derivative or second derivative test. Okay, I'm going to take a break now, go have some lunch, then we'll come back and do some more on another video.